Now we wrap up our discussion of Cauchy-Euler differential equations by talking about how to solve using odd either conditions. For example, in the example 6, what we're going to be seeing, which is this weird condition where we're evaluating using initial conditions at a negative input. And if you recall from our definition of a Cauchy-Euler differential equation, it because it has natural logarithms within it, it requires that x be greater than 0. So that is an important piece of a Cauchy-Euler differential equation, is that we make the assumption the argument is positive, mainly because reduction of order ends up with natural logarithms. So the other time that we have some odd weirdnesses going on is when we have what we would call a shift. But actually, technically, both of these are considered, in my opinion, to be transformations or shifts. Basically, our argument, what we're trying to solve for, or not solve for, but our argument for our coefficients, x squared and x's, they're just not standard x squareds, they're not standard x's, and again, our arguments may not be positive. So what do you do in these situations? Well, best thing to do is a substitution. So use substitutions. For example, if they give you an argument for an initial condition that's negative, well then instead of solving the Cauchy-Euler system or a differential equation with arguments that can be negative, x values that can be negative, we can let t equal negative x. So instead of y being a function of x, as we would normally consider, because x now is a function of t, we could say y is a function of t, and in reality, y is a function of t through x itself. So in those cases, you say you're originally working with dy dx, but in reality, you're going to have dy dt times dt dx, right? So that's the same thing as dy dx. It's just now we're considering y as a function of t, right? And then technically, because the way we've written this, t is actually a function of x. So maybe I should write it that way. Or t of x. Okay. Anyhow, so in this case, dy dx would be dy dt, but because t is equal to a negative x, dt dx is a negative 1. So you have a negative dy dt is the same thing as dy dx. And of course, that's dy dx is what these are right here and right here. We also need to know what the second derivative is. So you go ahead and take the second derivative. The second derivative, which we're going to need because of these guys right here, is going to be d squared y dx squared. And that's the same thing as saying the derivative with respect to x of the derivative of y with respect to x. But we've just shown that the derivative of y with respect to x is the opposite of the derivative of y with respect to t. So I'm just going to say the inside here, I'll highlight that, we're going to trade out for this guy right here. That'll give us, I need a different thickness, negative dy dt right there. Now we're going to make an assumption. This assumption we made earlier in this course that we had said something when you're dealing with exact equations, that the partial of f with respect to x, then with respect to y, if that's the same as the partial with respect to y, then with respect to x, then we have an exact. We call f exact. We're going to assume that we have a well-behaved function like that. Okay, so instead of taking the derivative of y with respect to t and then the derivative of that with respect to x, we're going to swap the order notationally, and we're going to say it's the same thing as the derivative, the negative derivative, because I can pull a negative out, with respect to t of the derivative of y with respect to x. And we happen to know dy dx, again, the stuff in blue, is just a negative dy dt. In other words, the negatives cancel, and we get that the second derivative of y with respect to x is the same thing as the second derivative of y with respect to t. And so if you start with an example like 6, where your initial conditions are negative, you can do a substitution like this, and now you're dealing with the following. Change back to green here. And your example 6, all right, down here, becomes slightly different. You have an x squared, second derivative of y with respect to t, though, minus, oh, and it won't be x, well, we'll leave it as x squared actually, minus 4x, and that derivative of y with respect to x that was in the original differential equation is now the negative derivative of y with respect to t plus 6y. However, we made the substitution here that t is equal to negative x, or in other words, x is equal to a negative t. So wherever you see an x, I'm going to replace that with a negative t. dy squared dt squared minus 4 times the negative t. And I'll actually say plus 4 times the negative t because the negative dy dt. And then finally plus 6y. However, I'm going to now run the negatives here, and this is going to be the same thing as t squared, and I'm going to have an abusive notation here. Y double prime minus 4t y prime plus 6y. The reason why I didn't want to, I just don't like to constantly use Leibniz notation. So really, in this case, we'd be solving t squared y double prime minus 4t y prime plus 6y is equal to 0. And when you go to solve this differential equation, your initial conditions are no longer y of negative 2 is equal to 8. You have y of 2 is equal to 8 because the inputs become negative, those inputs. Same thing here. Y prime of negative 2 will now be y prime of 2. So 2, 8, 2, 0. So y of 2 is equal to 8. Y prime at 2 is equal to 0. And then you would solve that differential equation. However, when you get to the end, dot, 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 you'll get something like y of t is equal to 6t squared minus 2t cubed, sorry. And now you can resubstitute back in, and you get y of x is equal to, remember, t is a negative x, so that's still 6x squared, but it'll be a plus 2x cubed. And then you should probably note to the world where x is less than 0. So that's one of the easier, actually I don't think that's the easier, I think there's actually a much easier substitution when you're not dealing with negatives. So this is the harder of the two substitutions, is when somebody gives you an example where the initial conditions are negative, so you just basically do a simple sub of t equals negative x. The other kind, which is example 7, what I'm going to do is I'm going to wrap that up, I'm going to pull that down to a different area so we can use it. So I'll just grab this and move it down the page a little bit, and then we'll use it. It's better than a whiteboard, right? So to solve this guy, again, I'll do a substitution, but this substitution should be somewhat obvious. At this point, we're going to just let t equal that x minus 4. And there's a couple ways you could do this. I would have actually done it this way in the last example too, but I just didn't think about it. But you could actually solve this for x if you feel like it. You don't have to, but you could. You could say, well, this means that x is equal to t plus 4, and then that would tell you that dx dy is equal to, actually, I should probably, yeah, maybe I won't do it that way just because I think that'll confuse people. I'll just continue the way I was going. So in this case, you have t is equal to x minus 4. That will imply that wherever you see a dy dx, you can say, well, I happen to know that. By the way, that's that y prime right there. I happen to know that that's dy dt, where t is a function of x. So it's the same exact argument as before, but these are kind of easier because if you look at the derivative of that t with respect to x, so in other words, take the derivative with respect to x on both sides, you just get 1. And so this ends up being just a dy dt. And then you can do the same argument as we did in the previous example where y double prime, which is d squared y dx squared, can be written as d dx of dy dx, and that's d dx of dy dx is now just a dy dt. No harm, no foul. We could swap those right there. So this is d dt of dy dx. And we have just shown that dy dx is, through this example right here, dy dt, sorry. And that's the second derivative of y with respect to t. So, this means basically we can make this substitution t is equal to x minus 4 without any harm. So now we're just solving t squared with an abusive notation y double prime minus 5 t y prime plus 9y is equal to 0. Again, it's a slight abusive notation, but not too much. It's just enough to be a little bit untrue. So t squared y double prime, technically y double prime was stood for the second derivative with respect to x earlier in the problem, but it's okay. We can still solve this. And as a final kind of hurrah, let's go ahead and solve this out. So we're going to change the characteristic, m times m minus 1 minus 5 m, and then plus 9 is equal to 0, which will imply that m squared minus 1 minus 5, which is minus 6m plus 9 is equal to 0. Oh, that's beautiful because that, I'm going to widen this out. It's kind of small for my handwriting. And I'll lose it too while I'm at it. That gives us repeated roots. So y sub c is equal to c1 x, oops, no, we're t's, c1 t cubed plus c2 natural log of t, and then t cubed. Just double checking all my mathematics. That's absolutely correct. Now, we didn't start in the world of t's, so we cannot end in the world of t's. We have right here that t is equal to x minus 4, so wherever we see a t in there, I'll replace it with an x minus 4. So that implies that our y sub c with respect to x is c1 x minus 4 cubed plus c2 natural log of x minus 4 and then times x minus 4 cubed. You should note here that there's a restriction that x must be strictly greater than 4, but that is somewhat implied anyway in the original problem. It can't ever be 4 because you'd be dividing by 0. And then when you were to solve this, because this is Cauchy-Euler, those arguments all must be positive anyway. So that's not much of a restriction in our case. And that's it. That finishes out all of Chapter 4. Exam 1 week from Monday. So Halloween. I think that's